All right, in this video, what I want to do is let's talk about section 6.3. Section 6.3 is all about talking about the exponential function and realizing that the exponential function is increasing or decreasing completely, depending on whether a is positive or between 0 and 1. So let's just stick to the function just for concreteness. Let's just stick to the function 2 to the x. And if we were to graph this function, which I think we did in the previous video, you would end up with something like this. So at 0, the function's 1. At 1, the function's 2. Oops. At 2, the function's 4. At 3, the function's 8, and so on. Okay, so we know all this. And then at -1, the function's 1/2, blah, blah, blah. So that's the function 2 to the x. And notice that this function is always increasing, and therefore it passes the horizontal line test. Therefore, it has an inverse. And the inverse is the log function. So in this case, it would be log base 2 of x. So in general, if f of x is a to the x, where a is positive and not equal to 1, then f has an inverse, and the inverse function is log base a of x. And this already tells us a few things about logs and exponentials that you probably already know, but I think are worth repeating. In particular, this tells you that if you were to take a to the log base a of x, you get x because they're inverse functions. And likewise, if you were to have log base a of x, log base a of a to the x, that's again x, again because they're inverse functions. Log base a of x, let's think about the domain and range here for a second. Okay, so if I were to take a to the x, so if we take our function f of x is a to the x, let me just rewrite it just to keep it better organized. The domain would be all real numbers, and the range would be the positive real numbers. Okay, not including 0. 0 is not positive or negative, so I say positive real numbers. Okay, so that's the domain and the range. Therefore, if I look at the inverse, that being log base a of x, the domain is going to be just the positive real numbers. Okay, you can't plug in negative real numbers or even 0 to a log. And the range is going to be all real numbers. And if you were to take, say, 2 to the x, we know what that looks like to graph it. Okay, we know that that's roughly the picture that we had before. And therefore, if we were to take the inverse function, remember what we do is we reflect this about the line y equals x. And so this is going to look something like that. Okay, and so that's 2 to the x and its inverse. And this is basically true for any exponential function where a is bigger than 1. Okay, nothing special about 2. Okay, a few different logarithm rules that I just want to bring to your attention. If you were to have log of a product, that's going to be the sum of the logs. Okay, I don't really care what the base is. You can write base b if you want. And what this is basically saying, just in logarithmic notation, so I actually, let's take one step back. If I were to write log base b of x equals y, this means that b to the y equals x. In other words, log base b of x is the thing that you have to raise b to the power of to get x. That's what log base b of x is it's this exponent to which you have to raise b to get x. And so this rule here that I have, that the log of a product is the sum of the logs, essentially corresponds to, if you think about it kind of hard enough, it essentially corresponds to the fact that when you multiply two things with a common base, you add the exponents. That's basically what this rule says. There's another rule for logs. It says that if you take the ratio, if you have log of x over y, you take the difference of the log. So this is log of x minus log of y. So log base b, just to be precise. And again, this is analogous to saying that if you were to take a quotient of two things with a common base, you subtract the exponents. And then finally, one other rule here. So one other rule is that if you were to have the log base b of x to a power, the power comes down in front. Okay, so you multiply by that power. And this essentially amounts to the fact that if you were to have x to the a to the b, then you multiply those exponents. Okay, and so that's what the rules basically say there. Okay, so these are kind of our three log rules. I'll put stars there. All right, and so those are the log rules. Now, a very special log for us is we've already seen e as a special number in regards to calculus. So log base b of x is called the natural log. Okay, so we write ln, it's French. Hence it's reversed. It's ln, not nl, but it's the natural log of x. Okay, and so just to repeat a few of the things that we know already. If we have the natural log of e to the x, that's going to be x, and this is true for all real numbers. Okay, so for all real numbers, x. This notation, by the way, means that for all values x in R. Okay, so for all values x in the real numbers. Okay, but this is true for all real numbers. Likewise, if you have e to the natural log of x, that's going to be x, and that's for all values x that are positive, because you can't have a negative or even zero into your log. Okay. If I were to have if I were to have the natural log of e, it's going to be 1. The natural log of 1 is going to be 0. And then I think it's useful, again, just to think about the graphs of these functions. This tells you basically everything you need to know. So y equals e to the x and y equals the natural log of x. Okay, I think that's useful to have kind of in our back pocket there. Okay, and then actually the line y equals x for this particular function goes right through the middle. And so these two functions never intersect, y equals e to the x and y equals natural log of x. They never intersect, but that's what they look like. Okay, and let's talk for a second about why 0 is not allowed in the log. Remember that we said in 6.2 that whenever we take an exponential, that's always positive. And in particular, it's never 0. Okay, and so it can never be negative. And that's essentially why the arguments of the natural log, or any log, have to be positive. And the reason for that is that if I were to write log base b, I don't even care what the base is. Let's give it a base, let's say 3. Log base 3 of -1 equals x. What is that saying? Well, that's saying that 3 to the x equals -1. But we just agreed that if I have an exponential function, that's got to be positive. And in particular, it can't ever be -1. It can't be any negative value. It can't even be 0. Okay, and so this is basically an argument that tells you why the input for logs have to be positive only. And that's because logs are exponents, and we know exponential functions have to be positive. Okay, and so that's that. That's basically everything I wanted to say about logs. What I want to do next, okay, and what we'll get into in the next video is to talk about the calculus part of this. Okay, so we've done a review of the algebra part, and then in 6.4, we'll start talking about the calculus part of this. What's the derivative of logs? What do they have to do with each other, and so on.